Hello, and here we go with week 11 in algebra. A friendly reminder before I dive into anything further, remember you do need to send me an email or message when you submit late work or redos. And this is for your own advocacy. Schoology does not let me know or do a good job of letting me know when you submit late work, so I need for you to let me know when you submit any late work or redos so that I know to grade it. So advocate for yourself. Just a quick message needs to be sent. Hey, Miss Cole, I redid Unit 3, Session 1. That's it. And now, let's dive right into our warm-up. So make sure you've got your math notebook out and you're ready to take good notes. This warm-up is we're doing rewind to last week and maybe even some previous math courses before this one. So I've got an equation below, y minus 6 equals 3x, and I need for you to rearrange this equation and write it in slope-intercept form. We like slope-intercept form because it allows us to easily identify the slope of the line. So after you rewrite this equation in slope-intercept form, I want you to tell me the slope of the line. Another reason we like slope-intercept form is it really quickly allows us to identify the y-intercept. And that's what you're going to do after you rearrange the equation in slope-intercept form, is also tell me the y-intercept of the line. And then once you have the slope and y-intercept of the line identified, it is really easy to graph the line, and that's the third thing you're going to do. So go ahead and click pause, try this in your math notebook, and when you're ready to check your work with mine, go ahead and click play. All right, I couldn't remember if I had a separate slide for this warm-up. So we're gonna squeeze it in right here. So writing the equation in slope-intercept form. So first of all, what is slope-intercept form? So remember, slope-intercept form is y equals mx plus b. That is slope-intercept form, where m represents the slope, so really that number being multiplied by the x term, that represents your slope. And then the constant term represents our y-intercept. So first, we just need to rearrange or rewrite this equation in slope-intercept form. So to be in slope-intercept form, we're going to have y all alone on one side of the equation and all the other terms on the other side. So right now, looking at this equation, it looks like we just need to move this negative 6, we need to move it to the right side of the equation. And to do that, we're just going to add 6 to both sides. And we will accomplish our goal. When we add 6 to both sides, we are left with y equals 3x plus 6. And I'm going to write that up here a little bit bigger. Y equals 3x plus 6, because we added 6 to both sides of the equation. So now we can quickly identify the slope. Remember, the slope is a number being multiplied by the x. So the slope is going to be 3. I like to write my slope as a fraction so that I have my vertical and horizontal movement. So we know 3 over the 1 is the same thing as 3. But I like to have it as a fraction so that I don't forget that there's some horizontal movement as well. Because if you have the slope as 3, remember that it's 3 over 1 so that we know that we're moving to the right one. So this slope tells us that we're going up 3 and to the right 1. That's what that slope tells us. What is the y-intercept of this line? It is 6. Our constant term is 6, so the y-intercept is 6. So now we can go ahead and graph this line. All right, so let's go ahead now and graph. So the best thing to do when you've got a line in slope-intercept form is to start with plotting the y-intercept. So the y-intercept is at 6. So let's go ahead and plot 1, 2, 1, 2, 3, 4, 5, 6. 6. I wanted to make sure I was at the right spot. So it crosses the y-intercept at 6, and now we're going to apply the slope. So we go up 1, 2, 3, and to the right 1. And we could do this again. 1, 2, 3, and to the right 1. Or you can go in the opposite direction as well. So the opposite of up 3, right 1 would be down 3, left 1. So down 1, 2, 3, and left 1. You can also apply the opposite slope. Down 1, 2, 3, and left 1. Once you have 3 or more points, you always want to have at least 3 points. We can go ahead and connect these points into a line. And there we go. There's our line. So you can see why having the equation and slope-intercept makes it a lot easier for us to identify the slope and y-intercept, which are key points to graphing our line. So I'm going to move on to this slide, next slide. So if you need more time, go ahead and click pause. Quick reminders for this week: make sure you're checking your grades tab frequently. Look for missing assignments. And if you have any, get those in ASAP. If you have any assignments that you started but didn't finish, go ahead and complete those as well. And then remember to make sure you're messaging me when you submit late assignments or redos. All right, so this week we are going to continue to look at linear equations, and this week more specifically we're going to look at systems of linear equations. So a system of a linear equation is when we have 2 or more linear equations that we have to find a solution that works for both of those equations, and we'll talk more about that in a moment. So we are going to look at transformations of linear equations, and I'm going to leave this one for you guys to explore on your own in Schoology. Because I don't want to take up too much time in these recordings. I can't cover everything from the week, but I did want to look at solving systems of equations. And 2 of the ways that we're going to explore this week are graphing and substitution. And then there's a third way to solve system of equations, which is elimination, and we're going to cover that next week. So 3 different ways, methods that we use for solving system of equations are listed right here, and the 2 we're going to focus on this week are graphing and substitution. So we're going to look at these 2 this week. And again, transformation of linear equations, I'm going to leave for you guys to explore on your own in Schoology, but I think I wanted to go over these 2 to make sure that you guys have a firm grasp on it before you jump into your lessons this week. All right, so systems of equations. So when we have 2 or more equations, we call this a system of equations. Here's an example right here. 2x plus y equals 5 and x plus y equals 2. So what's special about a system of equations is that when we find a solution, the solution must satisfy each of the equations. So we're looking for a value of x and y that when we plug them into each of our equations, they make each equation true. And that's what a system of linear equations is. So in this example, 2x plus y equals 5 and x plus y equals 2. The solution of the system of equations would be -1, 3. And that's because when we plug that value into both of these equations, it makes both equations true. Let's check that really quick. So remember, when we write our solutions as a coordinate, the first coordinate represents the x value, the second coordinate represents the y value. So I'm going to plug in to x. When I see an x, I'm going to plug in -1 plus y. I'm going to plug in 3, and it should equal 5. So, oops. And looking at that, I see that won't work. I forgot I had to add a negative in front of the 2 to make this work. Make sure if you took notes previous and wrote down this example, make sure to put a negative in front of the 2x. I forgot that I needed to add that in there. So now let's check our work. When we have negative 2 times negative 1, we get a positive 2. And 2 plus 3 does in fact equal 5. 5 equals 5. So that works. Now let's check when we plug into this bottom equation. So we've got x plus y. Well, x I know is represented by negative 1. Y is represented by 3 equals 2. I know negative 3 plus 2 is 2, so 2 equals 2. That's a true statement. So this solution here worked when we plugged it into both of these equations. And that's an example of a solution of a systems of equations. So again, please make sure that you add that negative in front of the 2x. I forgot to add that in there. So again, we're looking for values of whatever variables are being used that work for both of our equations. And that is a solution for the system of equations. I'm going to move on to the next slide, so if you need more time, go ahead and click pause. All right, so for systems of linear equations, a solution to a system of equation is an ordered pair that satisfies all equations in the system. We just looked at an example of that. So a system of linear equations can have exactly one solution. It might just have one ordered pair. It can have no solution. Sometimes there is not a solution that will work for our variables in each of our solutions. And then sometimes we have infinitely many solutions, meaning literally any value could work for that. And we're going to look at examples of each of these as we go through this presentation. So we're going to fill in some information over here in a little bit. So hang tight, but just wanted you to be aware that you can have one solution, you can have no solution, or you might have infinitely many solutions. So let's keep going with our exploration of linear systems of linear equations and solutions. So we've learned that a solution would have to work for both of our equations. So I want you to look at the systems of linear equations and then decide if the given solution is in fact a solution. So tell whether the ordered pair is a solution of the systems below. And if you want to click pause now and try to do this on your own and then check your work with mine, that's a great way to be more interactive with this. So if you want to do that, click pause now. All right, so to check our solutions and see if they work, we're going to plug the values into each of the equation and see if they work. So for number 1, 2x, x is 1, so I'm going to substitute in 1 for x, and then I'm going to substitute in the 3 for y and see if, oops, I didn't mean to put y, I meant to put 3, and see if that works for that first equation. So 2 times 1 is 2. 2 plus 3 is 5. So for that first one, it works. Now what about the second equation? We've got negative 2x. Well, instead of an x, I'm going to substitute in the 1 plus y. I'm going to substitute in the 3 and see if it equals to 1. Negative 2 times 1 is negative 2. Negative 2 plus 3 equals 1. Negative 2 plus 3 is 1. So this one worked as well. So yes, this solution, or this ordered pair, is a solution. So we would say yes for this first one. It works. Our second problem, our second system of linear equations. We're going to plug in x equals negative 3 and 1 equals y and check each of these. So y equals, so instead of a y, I'm going to plug in 1, equals negative 1/3 times x, which is 3. So now I know that negative 1 times 3, we can look at this as numerator times numerator, denominator times denominator. So negative 1 times negative 3 is positive 3, and then 3 times 3 is 3. And I know 3 over 3 is the same thing as saying 3 divided by 3, so we have 1 equals 1. So it works for our first equation. What about our second equation? Remember, these have to work for both. So we've got 4 times y, I'm going to plug in 1 for y, plus 12 equals 3 times x. I'm going to plug in negative 3 for x. So I've got 4 times 1 is 4 plus 12. I know that that's 16. And then 3 times negative 3 is negative 9. So do these equal one another? No. So this one did not work. So these are, this is not a solution. Negative 3, 1 is not a solution for our system of equations. So that's how we check if an ordered pair is a solution. You just plug those values right into both equations and see if it makes the equation true. I'm going to move on to the next slide, so if you need more time here, go ahead and click pause. All right, so again, how do we get to those solutions? So we were provided ordered pairs, but how do we get to those solutions? 3 different methods. Today we're going to focus on substitution using that method and graphing, and next week we'll look at elimination. So one way we can get an ordered pair solution is by substitution. So the substitution method works by substituting one y equal value into the other. So how do we do that? Here's the steps. So step 1, we're going to choose one of the equation and solve for either variable, either x equals or y equals. And usually there's a more easier way to solve for one of our variables. So we choose which equation is easier for us to solve for either y equals or x equals. Then once we've got y equals or x equals, we're going to substitute that solution from step 1 into the other equation. And then we'll solve the new equation, and then we'll solve for the second variable. I know, this is very arbitrary. So let's look at an example and apply these steps. It'll make more sense. So here's our system of linear equations, and we want to solve for x and y. We want to get a ordered pair solution. So for step 1, it says solve one of the equations, either x equals or y equals. Well, look, one of them is already done for us. So I'm just going to say, well, we already have that done. Y equals x, or I'm sorry, 3 plus x. So that was already done for us. Now we're going to substitute in that solution into the other equation. So what that is saying is that we're going to take this y equals, and whenever we see a y in the other equation, we're going to plug in x plus 3, because that's what y equals. Y is represented by x, or 3 plus x, and we're going to plug that in for y. That way we'll only have one variable to solve for, because remember, we can only solve for one variable in an equation. If you have 2 variables, you can't solve for them. But as long as you just have one type of variable, we can solve for it. So now I'm going to look at that other equation, the x plus y equals 5, and whenever I see the y, I'm going to plug in 3 plus x. So this it came from right here. And then we set it equal to 5. And if I want, I can plug in that top one. So we were plugging it, we changed the y into 3 plus x. And then we need to solve for this new equation. So now we're going to solve for x. So x plus 3 plus x equals 5. Oops, equals 5, not 6. So let's work on solving. I'm going to combine my x terms on the left side. X plus x gives me 2x. Oh, goodness. My pen was being silly, so 2, oops, it's being silly again. Let's get this going. 2x, there we go. 2x plus 3 equals 5. Subtract 3 from both sides. I get 2x equals 5 minus 3 is 2. I'm going to move back up here. I'm running out of space in this box. I want to keep it in this one box. Divide each side by 2, and I get x equals 1. Am I done? I'm not done. Remember, I need to have an ordered pair. I need to have a value for x and a value for y. I have an x value, x equals 1, and now I need to solve for the second variable. Well, look at that. Isn't that nice? One of our equations is already solved for y, which will allow us to easily find the value of y. y equals 3 plus x. I'm going to plug in my value of x equals 1 to quickly solve for x. And I get 4. So y equals 4. So my solution would be 1, 4 as an ordered pair. X equals 1 and y equals 4. So that is how we solve using substitution. I'm going to go on to the next slide, so if you need more time here, go ahead and click pause. Go ahead and maybe try this one on your own, where we want to solve this system, a new system of equations, using substitution. So go ahead and click pause and see if you can do this on your own. And then when you're ready to check your work with mine, go ahead and click play. All right, so first step, solve one equations for either x equals or y equals. So I'm looking at this second equation as the one where I'm going to either solve for x or y. This one would involve too much multiplication and work. It might get a little bit confusing. This one's nicely set up so I can quickly solve. I'm just going to solve for x. So x equals, I'm going to subtract y from each side. So I would get x equals 5 minus y. So now I'm going to substitute this into my top equation. So whenever I see an x, I'm going to plug in 5 minus y plus 3y equals 5. I need to distribute. So I'm going to have 2 times 5, which is 10, and 2 times negative y, so negative 2y, plus 3y equals 5. Working on, so that's it. I'm kind of doing now, I've moved on to step 3, where I'm solving this equation now. I guess I've kind of should move this down now, because I'm working on solving now for y. And now to solve for y, I'm going to combine my like terms. I've got negative 2y plus 3, so I'm really just have 1y equals 5. I'm going to subtract 10 from each side, and I get my final answer, y equal, not my final answer, I get my final answer for y, not my final answer though. So y equals negative 5. Now that I have my value for y, I can solve for the second variable. I'm going to plug in, I'm going to use my bottom equation. You can use either equation, but for me, looking at that bottom one, it's less work. So I'm going to plug that into that bottom equation, y equals negative 5. So I know one of my equations is y plus x plus y, actually I meant to say, x plus y equals 5. Now I'm going to plug in to solve for x that y is equal to negative 5 equals 5. And then I'm going to add 5 to both sides, and I get x equals 10. So x equals 10. So my ordered pair would be 10, negative 5. And that solution will work when I plug it in for x and y in both of my equations. And I can always check my work. 2 times x is 10, so that's 20 plus negative 15, because I would plug in y equals negative 5, and 10 minus 15 is, and I meant to say 2 times 10, which is 20. 20 minus 15 equals 5. So that would work for the top equation. When I plug in x is 10, y is negative 5, 10 minus 5 is 5, so that works. So you can always check your work to make sure it worked when you plugged it into both equations. You'll get more practice with that this week. And you're also going to learn how to solve systems of equations by graphing, which is why we reviewed how to graph an equation in slope-intercept form. So I'm kind of running out of time here. But to solve a system of equations graphically, you're going to graph each equation, and then wherever the lines intersect is going to be your solution. So solving by graphing, you just graph each line, and then wherever they intersect, that's going to be your solution. So remember, I said earlier in this recording that there's 3 different possibilities. Sometimes you're going to have one solution, sometimes none, and sometimes infinitely many. So how does each occur, especially when we're graphing them? Let's look at that. So if we've got, if we graph two different lines and they intersect, so if we graph two lines and they intersect, we're going to have exactly one solution because where they intersect is going to be our solution. So this will happen. We've got some clues that help us know when this will happen. So this is going to happen when we've got different slopes and different y-intercepts. So when you have different slopes and different y-intercepts, we know we're going to have exactly one solution. So that's pretty cool, that clue, because once you have your equations rewritten in slope-intercept form, if you look and you see, oh, I have different slopes and different y-intercepts, right away you know you're going to have one solution, and that solution will be where your graphs intersect. What about no solutions? Well, no solutions is going to occur when you graph your lines and they never intersect. And when does that happen? That happens when we have parallel lines. Parallel lines will never intersect. So if you never have an intersection, there's no solution. So this is going to happen when we have the same slope, right? Because parallel lines have same slope. So if you have the same slope, but then look, our y-intercepts are different, then if you have different y-intercepts in the same slope, you won't have a solution because they're never going to intersect. The last case is infinitely many solutions. This happens when you graph your two lines and you find out the lines, when you graph them, are right on top of each other. They're the same line when you graph them. So that means that any point on the line will be a solution. Any point that falls on the line will be a solution. That means infinitely many solutions. So this is going to occur when our line has not only the same slope, but also the same y-intercept, because it's the same line. So I wanted to share with you when you will have each type of solution, how many solutions, and then the clues that help us determine how many solutions we might have. So I'm running out of time here. I did want to go over solving by graphing, but I'm running out of time and I don't want this to get too long. So my biggest reminder is that when you're solving systems by graphing is to make sure that you have your equations written in slope-intercept form. And that is why I did that reminder in the warm-up this week, y equals mx plus b. When you have your equations written in slope-intercept form, it makes it so much easier to graph your lines. And then once you have your graphs, you can figure out what the solutions are. All right, let me put up your key phrase assignment. So we learned about systems of equations and what makes something a solution for a system of equations. So my key phrase question is 0.05 a solution for the system of equations below? And then make sure to tell me why or why not it is a solution or is not a solution for those systems of equations. Let me know if you have any questions and have a fantastic rest of your week.